now let's look at pressure increase with depth, or pressure of water that is stacked up, or actually any liquid. I will derive the formula, but it's a fairly easy one just to memorize, and I think it'll be very useful. Here is a volume of water. There's the area, there's the height. The volume is A times H. Next, I know the pressure is the force over the area. And the question is, what is the force? Well, the force is that weight of that thing, which would be mg over A. Next, we look at what the density is of this material. It is mass over volume. Now, I've just been gathering these formulas. Now, mass then is obviously the density, rho times V. Now, watch what I'm going to do here. I'm going to do some substitutions. For V, I'm going to put in A times H. So I have the mass is rho A H. That's the mass. Let me now put that mass in here. And now I have a formula. Instead of mg, it's rho A H G. The A's cancel out. And I'm left with rho GH. Very important. That is the pressure with depth. Now, it is the pressure, for example, in a water tank where the water is stacked up, and that would be the pressure at the valve. How high is that water stacked? And it's just rho, the density, times G, times the height of that water tank. It would also refer to pressure with depth. How much pressure is on a submarine at a certain depth? Rho, the density of the material, GH. So, one more thing is that pressure is rho GH. And that's actually called the gauge pressure. It's just a name given to that. And that's the pressure of, let's pretend it's a column of water on the ocean floor. But the absolute pressure is equal to the atmospheric pressure plus that rho GH. Because sometimes there's something else on top providing an additional pressure on that column of water. And if so, you have to add that in. And it's often the atmospheric pressure that you add on. So the gauge pressure is rho GH, and that factor's added when you have something else. A change in pressure at one part of a fluid is transmitted undiminished to all other parts of the fluid. That's called Pascal's law. In other words, if there's a change in one tiny area part, it transmits right through. Now here's a device filled with usually oil, and it's like a cylinder, and I can apply a force to one side of the cylinder. Here it's 100 newtons, and pretend it's a very small cylinder, say a square centimeter. That's the area. Well, the force is very easy to calculate, or the pressure is force over area, 100 newtons per meter or centimeter squared. And that means that that pressure is now applied undiminished everywhere through that entire little device. So on the other side, if I have 50 centimeters squared as that top, the pressure is still 100 newtons per square centimeter. Well, force, look at this, is pressure times area. Well, if force is pressure times area, look what happens. I can put in the pressure's 100, the area is 50. My goodness, the force on that side is 5,000 newtons. I'm applying 100 newtons, but I get 5,000 out because of this property of liquids. So here's a device again. The pressure that is in will equal, if I do some pressure in, will equal the pressure I get out. Pressure is force in over area in, which equals the force out over area out. And literally memorize this. That equals that. And that's called Pascal's law. Now there's one more topic called the equation of continuity. Suppose I have a volume of water, and I want to find the flow rate. How much water, a volume of water is flowing in time. Volume of time over time. There's the area, there's the distance. The volume then is area times distance. But now look at this. What is distance over time? Distance over time is velocity. Therefore, the volume flow rate is that area times the velocity. Now, if you have a larger area and the water then is moving into a smaller area, what happens is the volume flow rate has to be exactly the same everywhere. If that whole thing is filled and the liquid is passing through, what comes in has to be what goes out, meaning that the volume flow rate will be the same at every point. Therefore, this is the very simple equation. It would be A1V1 equals A2V2, meaning the wider the hose, the slower the speed. The narrower, the faster. Have you ever put your thumb on a garden hose and made it spray really fast? There's the formula, and it's easy to understand.